Hi, everyone, and welcome to AI Simplified.
I'm Allie,
I'm Phil.
And I'm Amjad.
and we're your podcast hosts. Phil, what are we going to be talking about today?
Yeah, today, Ellie, we are going to talk about deep learning in action.
All right, I can't wait. Let's start with a little introduction. Let's just jump right into it. Is there a difference between deep learning and deep supervised learning, Amjad?
Yeah, I know that those terms can be very confusing. So what we would do today is, I think first we should contrast with what machine learning and deep learning, or machine learning and deep machine learning, and then supervised learning and unsupervised learning. So just from a very high level perspective, Ali, uh, so machine learning is learning outcomes with data. Okay, and that has been around for, gosh, 40 or so years. So then what is deep learning? So deep learning is just a lot more data to learn from, a much bigger model to learn from. So we all hear these terms like neural networks or models. So really the difference between machine learning and deep machine learning is deep machine learning can take a lot more data and put it to good use with it. It also, the models, the brain, as an analogy, the network is much bigger compared to machine learning. So that is a basic sort of machine learning and deep machine learning differentiation. And then within machine learning, you have supervised learning and unsupervised learning, which we will today talk about. And then using our analogy from a minute ago, you can do supervised learning and unsupervised learning using normal machine learning, or you can do that with deep machine learning. So deep machine learning is just, bigger, faster, better. It is just like the modern version of machine learning. So that is, I think, an easy way to differentiate between machine ML, machine learning, and deep ML. So let's maybe now get into what is supervised learning and what is unsupervised learning. So let's go there. So let's talk about what is supervised learning first. In the context of business, we have a lot of attribute data. So a business is made up of products, services, customers for which we build those products and services, and people who build those products or provide those services. Just from a high level description perspective, most businesses can be described like that. And all these things, they have attributes, right? Products have their functional attributes in terms of uh, what they do. So let's take an example of a cell phone. It has a lot of features, and those are its functional features, functional attributes, right? uh, Customers, they have attributes. They are big or small. They are in this industry or that industry, or they consume these types or those types of products. Whatever those attributes are that define uh, these business dimensions. So if that is our sort of input space, then we, within our business life, we create human meaning with some outcomes or labels. So we label products as successful, not successful, mildly successful, or we label customers as high user of this product, low user of that service, profitable customer, not profitable customer, desirable customer, not a desirable customer, and so on and so forth. And many times, uh, these labels, they are human context, meaningful labels, but there is no direct sort of, rule-based logic that how all these attributes of products and customers uh, and people and services, how they translate into these outcomes. Uh, so machine learning learns that function. And how does it do that? So it needs a lot of data. So if you, within your organization have a lot of data as to how decisions are made, where you have uh, customers and you are offering them different pricing strategies and you are getting different outcomes. So a machine learning model can learn all that. I'll really dumb it down with a very simple example. So let's say the goal here is to decide which consumer is going to get a loan and which consumer is not going to get a loan. So you have, so consumers in this case, they are the customers, and they have a lot of attributes, their demographics, their income, their past purchasing behavior and whatnot. And then we know what decisions in the past we as people, we as humans, we as business analysts in that decision have made. Okay, we have given this customer a loan, we have not given this customer a loan, so we have that sort of a data. We also have their performance. So we know, okay, so this customer, have returned the loan or made their payments in time, but this other customer have not, and some other customer is in between. So that is what the labels are. Now your desirable sort of customers, high risk customers, low risk customers, medium risk customers, so on and so forth. All that supervised learning is, it learns with these examples. If you just say, look, in the past 5 years, we offered all these loans, these are the results, learn it. It will learn it. And now you throw the next customer, next consumer at it, and you say, okay, just a new consumer applied. It will take all the attributes of that consumer, run it through its calculator, again, simplifying things, and create an output and say, this customer is very likely to make all the payments on time. I am very confident about that. And then some human in a workflow can make a business decision as to whether to approve that loan, not approve that loan, fully approve it, partially approve it, whatever, right? So that is supervised learning.
Is it called supervised learning because there is some manual input into, you have to guide it into first understanding, like this is positive, this is negative? Because you can feed it data, but how does it know that that's a good thing or that's a bad thing? How do they know? How does it know if that's a good customer or that missing the payment is that a bad thing?
Yeah. So it is called supervised learning, Ali, because a human or somebody have made decisions. So we have all those decisions history available. It is generally called labeling of data. So that is why it is called supervised learning, that some subject matter experts, some expert have actually created a labeled data. And in many cases, it is, in a real setting, it is many, many experts within a company who have made all those decisions over time. And that is where I think the term supervised learning comes from, that it is labeling of the data. There is another example here, we'll go to that. So there is no conversation without cats and dogs. So there is, Phil, you have a slide where you have some cats and dogs and puppies and that kind of a thing. Why don't we go to that one? And that will, I think, maybe, yeah, so this one, that will maybe look a little bit less abstract. So think about the following supervised learning alley task for a software model or a machine learning model to learn. Is it a picture of a cat or a dog, or a cat and a dog, or neither? It is supervised learning. Why is it supervised learning? Because we have taken a lot of these pictures with all these different variations. One cat, two cat, multiple cats, one dog, two dogs, multiple dogs, combinations of cats and dogs, no cats, no dogs, bunch of other variations. And we as humans, we create a label for each image. And then, so now we feed, so the input in this case is all these images. The output is that caption, that classification, that label that a human or some process have created it, cat, dog, cats and dogs, neither, whatever, right? And then you throw a new picture at it that it has not seen before. And it would say, okay, I see a cat with 80% confidence, and I see a dog with a 95% confidence. And then your software, your workflow can make a decision. Is this a picture of a cat and a dog or not? I know that some of the work, Ellie, that you are going to show later, that involves makeup on a human face or maybe other forms of virtual try-ons. There, the software has to decide, what kind of a skin tone it is, what kind of light conditions it is. Is it a fair skin? Is it a dark skin? Whatever different skin tones are. And then you want to apply different products. You cannot apply the same product digitally the same way to every different type of skin. First, you have to decide what it is that you're looking at. So that is a very complicated example of supervised learning. So that is what supervised learning is, that we as people go about in the day and we take a lot of actions. An action is a label. We make a lot of decisions. A decision is a label as well. I'll give you another very simple example. So we apply to a university. So on our application, there is a lot of data. That is the input data. A lot of attributes, GRE score and this score and this grade and that grade and the quality of an essay, whatever, right? Somebody looks at it, maybe a committee, and they say, yeah, Amjad, you're not MIT material. We're not going to let you at MIT. But Ellie, you are. Ellie, you are admitted. Amjad, you are rejected. Well, as funny as that example is, maybe not so, that decision is a label. On my application, somebody is writing rejected, not admitted. On your application, Ellie, somebody writes admitted. Okay, so now let's say that thousands or tens of thousands of applications are processed that way, that experts have looked at these applications and have applied judgment to it. I'm sure they're using some criteria. Some of it is expressed, some of it is tacit, some of it is not expressible, there's some quantitative aspect. But what machine learning does is say, okay, I don't have to go ask the committee that is making these decisions. I know they are looking at this input. And for each input, they made this decision. I have all these examples. These are my training examples. I'm going to use that to train my brain. And nobody is telling me how they were using this input to compute that output. That is my magic. That is my, if I'm a machine learning agent, that is my competence without comprehension. I don't need to comprehend. I'm just going to build a competent skill that I will make the same kind of decision that you guys are. So now then comes the real life test. So now you say, okay, now here's the next application. The committee independently decides, and the AI, in this case, supervised machine learning, independently decides. And if AI has learned all of it correctly, the committee comes back and say, admit it. And the AI also say, admit it independently. Mm-hmm. So that is a sort of, test that it has learned that skill. So that process, which is making that decision, and we sometimes use this term label for decisions and actions, that's just a computer science kind of a funny lingo. But that is really what it is. And we can have hundreds of or thousands of examples from practical life. I'll give you another one, right? So just while we are at this topic, because I think it's a very important topic. So now let's say that the setting is a hospital and it is radiology, and you're looking at somebody's x-ray, and a radiologist makes a determination that, okay, I am seeing this in this x-ray, and I, as a radiologist, I write a little report, which then goes to a physician or a surgeon in the next workflow. There is always a workflow. Nothing is in isolation. Okay, but this function, I'm looking at an x-ray and I am writing an expert narrative as to what it is that I see in it. So I am an expert as a radiologist. I have gone through a lot of undergrad and grad school training and then residency and all that to get to that point where I can read an x-ray and I can write a report that what is it that x-ray is telling us in a very sort of accurate way. So in this case, what is supervised machine learning? If you have examples of a lot of such x-rays and reports written by radiologists, you will feed it to a supervised learning brain, and it will learn that. It will learn to become the world's top radiologist. Now you give it the next x-ray that it has not seen in its training. It will write, it will create an accurate diagnostic narrative that is what I see in it. And its performance would be very comparable, maybe in certain cases, even better than a human radiologist. Again, we are not making, in our human-centered approach to things, we are not making any sort of, suggestions here. Humans are always going to be in the loop because none of these things are perfect. AI is not perfect. You will hear things like, oh, my model accuracy is 80% and 85% and 90%. And then, it decays over time. And then I have to retrain my model and all that good stuff. That's very true. So there is no such thing as 100% accuracy. Even human performance, even for experts like radiologists, their performance is not 100%. We all have to work in teams. Even AI and people have to work as teams. We have to check each other's work because people's lives are at stake. A patient is expecting the right diagnostic. A person needs that loan that has to be approved in order to help that person achieve his or her goals, right? These are everything that happens in business life or in life in general, at the end of the day, is affecting humans and their quality of life. Eventually, when you track all these decisions down at the end of it, there is, a human and sometimes an animal, who is the subject of that decision that has eventually reached that person, right? So anyways, so my point is, this is really, really important stuff. So deep supervised learning, it's a tool. So now let's say, just using my radiologist example. I am a radiologist. I have finite number of hours in a given day. If nothing else, this is a productivity enhancer tool. If I was able to read 10 x-rays in a shift, maybe now I can do 100. Or AI can check my work, or I can check AI's work. And if AI and I, we both arrive at the same conclusion, then we are making a right decision. We are making a right diagnosis. It is going to positively impact somebody's life in the downstream workflow when that decision reaches in the hand of somebody who is going to take further actions upon it. The beauty is, like human brain, the brain that learns any of these things is exactly the same. Same algorithm, same structure. So that is the beauty, that a deep supervised learning brain can learn any input output combination, whether it is a, consumer loan approval, or figuring out how well a new product is going to do in the market, or what is in this x-ray. Same, almost the same architecture can learn all these things. So that is another sort of beauty of deep supervised learning. And we'll talk about, uh, how do you build competencies and skills, and combine them into other higher level cognitive functions. But that is supervised learning. So ask me some questions in terms of,
Although this really excites you, Amjad. So when it comes to considering any of these examples, how is the how are the deep learning models trained? How's that training completed?
So look, I think it's a it's a little bit of art, a lot of science, as I think, as your slide kind of says. It's not really one thing. It's an iterative process as well. But at the end of the day, one thing is for sure: it is an engineering process. Challenge, or most of the work, is getting the data, the input data and its labels in the right place. As I said, that the deep learning models, algorithms, that brain part, that is pretty much the same in every case. Now, the model training, so that it is learning the right thing and not sort of doing an incorrect learning, there is a lot of engineering involved with that. And I think that, so data preparation and then the actual observing that how a model gets trained, that I think is where a lot of engineering and craftsmanship comes in. Sometimes you end up training, Phil, many different models under different variations, and then you vote or consult these different models, and you take their outputs. Like you have 10 models, and you ask, you feed your x-ray to each one of these 10 models and see what do they say. And then you kind of weight their input, and then you try to draw a meaning. One thing is also for sure, in most practical applications, there is a higher level supervisor model, uh, as well as some human oversight in the mix as well. So I know that, we always sort of, in our software life, we talk about level 1 and level 2 and level 3. Oh, I'm an L1 team, oh, I'm an L2. So if, using that analogy, if these machine learning models are L1, you do need an L2, uh, an L2 AI to check the work of an L1 AI. And then in many cases, there are certain things that go to a level 3, which in many cases is a human in the loop just to check. And again, based upon how confident level 1 was about a certain outcome, decides that, hopefully you want, like in any engineering situation, 80% of the work to be handled at level 1 without it ever have to go to level 2. And then, very few things go to level 3, and mostly it is people at level 3, and they are figuring out how to continue enhancing and making these models, better and better over time. Because the moment you put a model in production, if it is, batch mode trained, meaning you train it once and then you put it in production, new variations are going to enter into the environment and this model is going to lose its efficacy. In future episodes, we are going to talk about learning architectures where we want these models to learn on the job. So, but that is not easy, and we'll talk about those challenges in some future episodes. Today, mostly, what happens with the deep supervised learning is you train something, you put it to use. Now, while it is being put to use, it is not learning anything new. It is just working, working. Taking actions, making decisions, whatever its work is, right? But meanwhile, all the new data that is coming in that it has not previously seen during its training, we are capturing all that data. And in today's sort of mainstream deep supervised learning, you retrain these models at some frequency, monthly, quarterly. Very rarely they are weekly or less. Most point is these are all batch mode trained models. Train them once, put them to use while they are working. They are not learning anything new, and that kind of thing. And then every once in a while, you retrain them, and then you put them back there, and that kind of thing. But that has to change as time goes by, and we'll talk more about it in our future episodes. But it is a lot of engineering, both on the data side of things and how these models get trained. I'll give you an analogy. So at some level, uh, if you just imagine a wonderful and very complex mountainous terrain, that is kind of what the training landscape looks like. That you have a lot of these peaks and valleys and very rough mountains and not smooth at all, right? And then, so just a lot of these cones, right? So if you sometimes see these National Geographic movies going over, Alaska or Siberia or whatnot, so you see these cone-like structures. So that is kind of what the landscape of a training model in that high dimensional space, that is what it looks like. So the job then of a training algorithm is, no matter where it starts from, is to find its way into some local minimum, where the analogy could be the valley, where you find some stable point. So maybe some oasis there and some rivers and streams and whatnot. That is what the training algorithm and the people who are supervising the training process, that is what they are making sure that that's what happens. So that, I think, is where today a lot of the effort, so all of our colleagues who are quote unquote ML engineers, that is what they are doing. Because look, I will say one other thing. we talk a lot about machine learning and deep supervised learning, which is a branch of machine learning, right? Machine learning does not mean that you're learning correct stuff. You can very easily learn incorrect stuff. You can very quickly learn to make bad decisions, take bad actions. So my point is quality assurance, quality control is so hugely important uh, because these things can operate at a superhuman speed, and you cannot afford mistakes uh, at that point. I'll maybe one more example of supervised learning in action, and then we'll let Allie take us through her demo. Then we'll talk a little bit about unsupervised learning. There's no conversation on machine learning can be complete unless we contrast between supervised learning and unsupervised learning. So in all these uh, autonomous driving sort of applications that are coming with Tesla and others, that computer of the car has to make a lot of decisions in real time and have to keep making those decisions on the road, not on the road, in the lane, not in the lane, object in front of me. Is it a pedestrian? Is it not? You know, is it a kid? Is it an adult? Because kids and adults behave differently. So these are classifications that supervised learning model has to make. And then it say, okay, I'm in a lane, I'm in a highway, I see a kid in front of me. What is the probability of seeing a kid in front of me in the middle of a highway? Very, very low, but I'm seeing one. I need to do something urgently. I need to stop. This is a very unlikely situation, but it is in front of me. I have to believe that what I'm seeing is correct. Uh, while it is probabilistically very low, it is right in front of my eyes. It is happening here. I need to do something. So just think about the complexity of that. I'll give you another sort of the last example, I promise, and we'll continue with this discussion. Think about the following. We are living in the uh, COVID arena, and uh, we talk a lot about, you know, vaccinations and immune systems and whatnot. Okay, so we as people, roughly 100 billion neurons, and we are able to make complex decisions and what have you. And a neuron sort of finds a cell, so a computational cell, but still a cell, right? Okay, now let's just talk about in human body, one cell, okay? All kind of stuff, it's coming its way. It has to make decisions. Is this thing that just got in here, is it good or is it bad? Think about how difficult that decision is if you are just a cell. You don't have 100 billion cells, you're just one cell. And you have to decide, is this thing sugar or oxygen? Or is this something bad that has entered? Or this thing that has come, is it part of me or is it not part of me? How do you make that decision? It's not an easy decision. So if you think about, if you are just one cell, every cell in human body, you have to make those decisions. Part of me, not part of me. That is supervised learning. That is a classification decision, right? So training of the immune systems, the design of vaccines and whatnot. Uh, just think about how much of these concepts have to be in play. Point I'm making is supervised learning is everywhere. Wherever you see, you know, we as people, as conscious beings, we have to, we are making decisions and we want AI to learn to make that. But everybody else, cells in our body are making those decisions. You know, shall I let this thing that I've entered stay or shall I attack? That is a decision. that it has to chemically make a cell. Plants have to make decisions. Animals, large, small, have to make decisions. Businesses have to make decisions. And deep supervised learning is okay, I can learn all that. And I can make those decisions faster, better, cheaper, and I can become a productivity enhancer tool. We together can make smart decisions. So
To that point, Amjad, where would you say deep supervised learning is in comparison to a human's ability to make those decisions as
yeah,
compared today?
so I think that there are two sort of sides to that, and I know that you have, I think, a slide on that one as well. The There are sort of capabilities that we have. So, like, just let's pick one: our ability to see, perceive life around us. Right? Our consciousness is mostly electromagnetic in nature, so we mostly perceive the electromagnetic uh, spectrum around us. So, in simple words, it's light and light bouncing off of different things and whatnot. And then we, perceive it, we call it seeing. So, machines' ability to see like people has become very good, not at a uh, human level yet, but approaching vastly there. So there are capabilities that we as people have, and deep learning, I believe, in 5 years or less, will surpass. The deep learning would be able to see better than we can see. So whatever we as people call seeing, deep learning would be able to see better. So that's one example, one types of competencies. Now think about it. If we just ask each other, how do we see? So we have a competence called seeing. I think unless we are a sort of, vision PhD and that sort of a thing, it would be difficult for a normal person to describe how and why am I seeing. But we are seeing, we can perfectly see, this is a bottle of water, this is my computer, that's Phil and Ellie on the screen, and Ellie has this nice background. Okay, so, but how are you doing that? I have no clue. Competence without comprehension. I have competence. I have no comprehension. I can't tell you how am I doing it, but I'm doing it. So machines would be able to do the same competence without comprehension in 5 years or less better than people, same or better. Then there are all these other things that we as people, you know, uh, can't do. Uh, so looking at extremely complex, high dimensional business data, we can't visualize all that. And then making decisions based upon whatever the patterns are there, uh, and those types of things. And there, certainly, we as people today can't uh, do that part because we don't have those non-human powers of the AI, which we talked about in the last episode. So there, that is already a strong team building thing that the AI of today, when it uses its non-human powers like ability to visualize a lot of data and then applies this deep supervised learning to it, there now it is doing stuff that we as people cannot do. But for people skills, I would say, Phil, in 5 years or less. Look, I'll give you just sort of another example. So the most recent rover on Mars, think about how many decisions it has to make as an autonomous entity. You know, shall I move? Shall I stop? The horizon over there is very different from horizon on Earth. Gravity is less than what gravity is on Earth. And it has to decide, what is it that I'm seeing? What actions do I take? Can I recover from those actions if I have to? Just imagine the amount of artificial intelligence that goes into creating an autonomous entity that is in an alien world by itself. Maybe few of the rovers that we have sent. Uh, so now I would call that a non-human power of AI. Now, certainly there is a lot more engineering than just AI. And as we have talked about, AI is just a tool. But that rover, its brain, that is the narrow AI of today. Uh, we cannot send a person there yet because we are fragile. You know, we break too easily. Uh, Radiation kills us. There is no quality of life on Mars. Then our consciousness would say it sucks as an experience. Luckily, the rover on Mars doesn't feel a thing, thank goodness. And it is making all those smart decisions, right? So anyway, so I think we are fast approaching, Phil, where uh, these uh, machines' abilities for the type of things that we can do, our own sensing and perceiving, seeing, hearing, you know, touch part, the complex things that we do, as a normal example, drive cars, make business decisions, analyze stuff. They're going to be, right there with us, and it's awesome because if you build the right workflow, then they are tremendous productivity enhancer and creativity enhancer tools.
But how many decisions, how many actions are actually needed for a brain to reach, or like a supervised learning brain to reach competency? Because I mean, you mentioned some pretty varying levels of competency. Self-driving car versus determining if someone on an application is qualified. It seems like there'd be vastly different needs in terms of data or labels, which you mentioned, to get to that point of competency.
Yeah, no, look, if you, I'll give you a very simple example. So you have to compare everything with something else. So in case of AI, the most normal comparison is modern human brain. Okay, so we have about 80 billion neurons. The neocortex, that top part of the brain, which is like a little sheet, uh, covered sheet, right? That has, give or take, let's just say, for the sake of this discussion, 25 billion neurons. Each neuron have maybe 10,000 connections. And so it is big, but it is not that big. Here's the interesting thing. Those neurons are grouped in columns of 100 or so neurons each, and pretty much they all do the same thing. So they have the same method, same algorithm that they are using. So in terms of the a machine today to reach that point, and some people call it singularity, and I really don't like that term. I think we are 10 or less years away from machines to be more powerful than human brains. So it's 2021. Before 2030, we will have computers that will have similar architecture, neuromorphic architecture like human brain, and they would have same computational capability that brain does. And in other terms, they will have a lot more capability that human brain does. Because even today's, at some level, our cell phone, which is a computer, is differently architected than human brain. And in its architecture, it is a lot more powerful than human brain. But it is not human brain. It is not structured like human brain. It is not wired like human brain. It cannot do what human brain does today effectively or efficiently. So imagine the future computer is the artificial computer or the computer as we know it today, plus a neuromorphic part of it, which is the brain-like part. So the computer of today, for the things that it does, it already is a lot more powerful than human brain. But it does not, it cannot do what human brain does today, effortlessly, you know, the way we are able to, see and hear and feel and talk and those types of things. So that neuromorphic architecture or computing, I believe, in less than 10 years, will have that as well. So then now you are going to have a machine that, is going to have a brain like us, not consciousness yet. So I'm going to keep making that point. And it's going to have all this other computational power, meaning that it can have a lot of competencies in terms of the types of things that it can do. So it is Ali coming, and I'm not saying that in 10 years it is going to be in the hand of every consumer. That maybe 20 years out, maybe, because eventually, we live in the age of consumerism. So eventually, if one day, AI is all out there in every computer, in every device, so then, eventually we are going to stop saying the term AI. It just will be our sort of, computer and whatnot. And then my prediction there also is that, computers are going to disappear. Meaning, if you think about it, Ali, 20, 30 years ago, they used to be bulky, right? So now they are slick. And now most people just have smartphones. They're getting smaller and smaller. Eventually, they are going to disappear as well. So, it's going to be wearable in our glasses, or, it's going to be it's going to be more virtual and less device sort of thing. Now, of course, the the computation has to run somewhere, so it will run in the cloud and what have you. But we as people, it will not feel like that we are carrying bulky devices with us. Now, we will have, because we will need physical beings like us. So we will see a lot of social robots entering into homes and workplaces and whatnot. That we will see, but we would not be carrying bulky devices on us. They will just sort of become part of us. A little cyborgy future there. And not in an intrusive sense. So I think initially it just would be, so whatever it is that we are wearing, computing is going to be just embedded in.
Fascinating.
So I think maybe, Ali, with that, maybe you can change the topic a little bit, and you can show us some of your stuff that you are going to show, and then I will point out that once you show it, that which part. So if you maybe just, as you show, just give me some airtime, then I'll kind of talk about that, what type of AI is making that experience happen. So
Okay, sure.
Over to you, Ali.
Sure. So first, I'm actually going to start with the facial landmark tracking. So what you're seeing are some of the points on the face that this particular model is seeing on my face. It's not tracking all the points, but I wanted to show you this first so you can see really as my mouth is opening, as my eyelids are opening and closing, it's able to see that motion. So this application or this technology could translate into a number of applications, but today I wanted to show you specifically a front-end application, and that's makeup. So we're going to
maybe want to, Ali, just want to go back to where you were a minute ago. I just want to make quick. So here, so just imagine this is real feed, and this program is able to, first of all, find a human face, in this case, your face in the frame. And it also knows what all these different facial landmarks are, if I may call them that. And it is able to track it. And as you are, Ali, maybe moving right or left, as you are moving your, it is able to track it. So that is real AI in play. There is a lot of computer vision here. There is a lot of deep supervised learning. Certainly, we can talk here a lot, but we don't have to, that somebody spent a lot of time building training data sets and going through all those things that we have been talking about for the past hour. But just this thing that you're showing, Ali, that is only possible because we are combining uh, computer vision with deep supervised learning. So amazing. Please continue.
Uh, yeah, so in application or utilizing that model, so we've said, okay, when something is on this particular portion of an eye, now we're going to use this to apply makeup. So uh, it's pretty impressive because we can take something like, you can just see here, these are would-be makeup shapes. And I'm building out an eyeshadow. And I'll show you this live as well with a real product, which is pretty fun to watch. But first, you can see how, ooh, that's scary. Let's use how you could see, and just the different shapes can even be placed on an eye. And each color is, even though it's applying the same color, it's using a blending algorithm so that it's taking into account the transparency of the color and the underlying skin tone. In the lighting condition, so that it's giving you a very real experience. So just as a eyeshadow of this color would look different on every single one of these models, in real life, it's taking into account all the real features and displaying it as it would in real life. So you can see here the ability to do this is because the model has been trained to say, when you recognize somebody right here, you can place this eyeshadow. And that's where a light wash eyeshadow should go. And when I tell you this color, it's going to place it there. John, did I explain that properly?
Yeah, I mean, again, please keep going. This is just, again, you can see now, that how all these concepts that we talked about, that this AI is making these complex decisions and figuring out, what to do. Now, this is perfect, Ali. I'm amazed. Please keep going.
Yeah, I'll show you some other colors. These aren't very good colors for obviously every model, but you can see there are so many points on the face. It's even able to, point out exactly where a blush should go, or it's going to take the outline of the lips and it's going to place lipstick on the lips. For every person, each person has different shaped lips, but it knows because of the outline and how it's been trained that it can apply eyeshadow on the where it should go, blush, lipstick. So those are a couple of the, how the shapes translate into or onto the model. This is pretty fun too. It's more fun when you can do it in a live environment. So I'll just show you here, in the same way that we use a still image, I can choose any lip color and it's going to track with my lips. It's going to use the outline in real time.
I mean, first of all, Ali, I would say that the quality of this digital experience is amazing. And look, I mean, this is the beauty of real AI in action. I mean, this experience, and I'm not, a makeup expert, but certainly, makeup is something where you are looking for perfection. And we all know that AI is not perfect, but yet this experience that you are showing us in real time, that to my human eye looks very perfect. So Phil was asking this question earlier, that can AI do stuff that at a human level skill? So this certainly is an example, of maybe better, but I'm just amazed with the quality of this digital experience.
So I'll take it one step further. So I showed you models, I showed you this in real time. Now I'll show you something that takes it one step further, and that's utilizing a real product and AI, and you can compare the two. So we'll use the example of this kind of eyeshadow uh, stick. I'll just lightly rub it on. And forgive me for being a little no mirror here. And now I'm going to choose that same color, but I'm only going to put it on one eye. So now you can see I probably didn't go dark enough on this one eye, so I'll just darken it a pinch. And I'm going to actually bring this up a little bit. So now when you're looking on left eye and AI, so left eye is real, the makeup is still there, and right eye is the AI. So
I cannot see the difference between the two. So you have, on one side, a physical product applied. On the other side, you have a digital product applied, and they are creating an integrated experience. And that is like beyond amazing. And in this day and age of post-COVID world, I know how important uh, contactless and a safe way to try products in the comfort, safety, security of our own, work or personal spaces is. So this is just like amazing. This is adding, this is certainly increasing the quality of consumer experience, and then in turn the quality of human life. And if we can just extrapolate that what these sort of technologies can do, if we can just imagine many different applications, many different use cases, sky's the limit. So that is where, I just get super duper excited. And I think, Ali, one thing that is super testimonial here is, look, in all these examples that are meaningful, there is always a human in the loop. When these technologies are designed to be human-centered, then the outcome is truly awesome. So that, I think, is our message that we'll keep reiterating, that from a design perspective, human centricity really helps you achieve those optimal outcomes. Truly, truly amazing, like mind blown, totally mind blown. What do you think, Phil?
I can't tell the difference. And to your point, I feel like a technology like this, especially in our post-COVID world, will bring so many more options to consumers, and also will help help businesses put more tools in their products and product offerings.
Yeah. Awesome, awesome. So I know that we are kind of a little bit out of time. I'll just take Phil 1 minute to talk about unsupervised learning. We have been talking all about supervised learning. So if supervised learning now is bringing human context into the picture, meaning, we outcomes that humans want, decisions, actions, right? Then unsupervised learning is you remove all those labels and you just look at the data and you see how is the data naturally organized, and does it fall into some groups or segments or clusters. So in supervised learning, we can take data and we can apply, labels to it, right? So if it's a customer data, we can say profitable customer, not a profitable customer, right? And we get like those two groups of data. And that is a human meaning, profitable customer, not a profitable customer. That is a human context sensitive stuff, right? That is kind of where the meaning is all human centered there. But if we don't have that, and if we just have the customer data, and we just see what its natural organization is, and are there any groups or clusters there, that is what unsupervised learning is. So in many cases, in the narrow AI of today, unsupervised learning is a sort of precursor to supervised learning, where you just do data exploratory analysis and you see uh, how is this data how is this data organized. Sometimes you are able to just have more variables or less variables and see what their natural organization is, and it just tells you about the data and its nature, and it informs you what types of models, supervised learning models, are possible with that. And they kind of work in conjunction with each other. But the real deal of narrow AI today is deep supervised learning. And we'll, in our future episodes, talk a lot more about architectures and complexities and pitfalls and issues and all other fun stuff. But I think it's a good stopping point today. We talked quite a bit about deep supervised learning. So now, one thing that we always say is, okay, so what do we do? So I think that if you are a business, first, you again take a look at, are you doing any unsupervised or supervised learning in your business? If not, identify workflows or cases where supervised learning can help. And that is a good starting point. Start simple. Wherever you are making some high volume, low complexity decisions, that is a good place in a business to start from a supervised learning or deep supervised learning perspective. Uh, High volume decisions, low complexity. So, and we can certainly, in our future episodes, we'll talk about what are in different industries, what are the examples of high volume decisions, meaning a decision that a company has to make a lot a given day or a given week, and its complexity is low. So that is a wonderful first case to outsource that. If we are going to start thinking about AI as our extended minds, extended colleagues, and we are outsourcing this work to these wonderful new colleagues of ours, who luckily are not conscious. High volume, low complexity decisions. AI can learn that very quickly, automate it, free up a lot of the time in an organization for us to work on other things that AI cannot work on. So that's my sort of, message for the business on a supervised learning journey. If you already have started a journey and you are further along, then just take a pulse check as to what your successes and failures and learnings have been to date, and then where to go from there. You will find one common pattern that a lot of time goes into getting the data in the right order. Then your engineers have to spend a lot of time training these models and putting them together. Then they have to be inserted in some workflow, because they are just one cog or few cogs in a bigger picture or in bigger architecture. With that, Phil and Ali, over to you.
Well, thank you, Amjad, for talking to us today about deep learning in action. Really good chat, and I look forward to our future episodes. Definitely stay tuned.
Absolutely.
Looking forward to it.